So you can see my Christmas present to you here. Fa la 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 la. So I can. All right, I kind of have this belief that a break is meant to be a break. So that's what it is. Aren't these fun to play with?
I love those things. Put it in your head.
Then you always have to put your...
Oh, he goes like into the sphere. Hamster ball.
Yeah, I've seen those, right. All right, so I bought this because it was just fun. But then I realized that it portrays perfectly the example of how related rates work, okay? Because we did the sphere problem on Friday, okay? And so I'm going to just run through that really quickly. The volume of a sphere has a formula 4/3 pi r cubed, okay? So if we take the derivative with respect to t, okay, that means that the volume and the radius are both functions of time, which means their values are dependent on time. Then the derivative would be dv dt. Remember, dv dt, we would call it as the rate that the volume is changing by, okay, is equal to, then do the math here, it becomes 4 pi r squared times dr dt, where dr dt is the rate that the radius is changing. So what's cool here is if I could, as I move the radius, if I make the radius grow, we know that the volume also grows. But they're actually related. And this is the formula that relates the volume, the rate that the volume is changing by, with the rate that the radius is changing by. And I don't know if you've ever noticed that, like even if you're blowing up a balloon, you know, if you're blowing it up yourself, you notice that it starts off, it grows kind of fast. And then after a certain while, it feels like you're blowing into it and it's not going anywhere, not getting any bigger. Okay, even if you're doing one of those tube things like growing up for a graduation party or something. And the reason why that is because the volume, okay, is the rate that the volume is changing is dependent on the radius of the sphere at the time. In fact, you square the value of the radius, you multiply it by 4, and then multiply it by pi, and then you multiply it by how fast the radius is changing, and that tells you how fast the volume is changing by. So the bigger the radius, the faster the volume is growing, which gives it that impact like this, vroom, you know, which shows how fast it grows. And so that's why if you want to reverse it, if you're blowing air into this, dv dt is a little amount, which means the radius is just going to move a little bit about. Okay, see if we work it backwards. Now, by the way, the surface area, okay, surface area of a sphere is 4 pi r squared. Anybody know that one? That's the formula there. 4 pi r squared, that's the surface area. And so if you had the actual amount of surface area around the sphere, the rate that that's changing by is 8 times pi times r times dr dt. So the rate that the surface area is changing by is that. Anybody notice anything interesting up on the board? What do you got? Start off with the volume. 4 pi r squared times the rate that the radius is changing, which is the formula for the surface area. Okay. It also fits in with the area of a circle. If you just took a plain old circle, hey, that one wasn't bad.
That's a good one.
I'll take that one. Area is equal to pi r squared. Okay, this is like the pond problem. The derivative of the area with respect to time is 2 pi r dr dt. So what happens here is the area is changing at a rate that is dependent on the circumference. Okay? So that's the deal there. Okay. Well, we're going to go through at least 2 different problems today. I've got a little bit of demonstration here for you. So let's look at number 4. It's the ladder problem. All right, let's do the ladder problem. Go read the ladder problem, and then we're going to set it up. Yeah, I think I'm going to move this down. Okay, so we're gonna start this off by doing the way that we would do all related rate problems, but then also this is a good idea to do this for lots of different kinds of problems. I find myself using this technique for solving lots of different problems. Identify what I know, what I want to know, and then, in this case, an equation that relates the variables. Okay. And then some sort of diagram or picture helps. So we're going to identify those. Okay, fill in all of those that you know. Okay, and then I'll take some advice here. Okay, I'll start taking anything from anybody. It doesn't matter where it belongs. These problems don't have to be done in any order when you do this. So give me something. Give me something. Yeah. Okay, so 17. So I'm going to start drawing this picture here. It's leaning up against a house. So I've got the house here. And the ladder is leaning up against her. Okay, and the house and the ladder is this forms a right triangle. That's kind of a key thing. So this is 17 feet. Okay. Yeah. Okay. So if I label this as x and this as y. The equation x squared plus y squared now equals, it's going to be 17 squared because the ladder doesn't change. The ladder stays 17 feet. So it's x squared plus y squared equals 17. Okay, what else do we know? What else should go up on the board? Okay, so this thing goes out this direction 3 feet per second. So the base of this thing is 3 feet per second. Okay, so 3 feet per second is something up here. Based upon my diagram, what is 3 feet per second? dx dt. Okay, so this is dx dt, the rate that x is changing by. Okay, very good. We're getting there. I don't think we can solve it just yet. In fact, I don't even know what we're solving for. Yeah. X equals 15. That's at the moment that x equals 15 is the moment that we're trying to figure out. So that's x equals 15 feet. Yeah. So how do I say that? Good. So the all glorious dy dt is what we're out to figure out. Okay? Which is the rate that y is changing by. Okay? So we can go ahead and solve it. All right. See the ladder? All right. So I just tested it outside, and it will fall to the floor, but we got a rug carpeting here. So if this were to slide, this thing falls, hits the ground. Okay? This is the thing. This is what's going on here. 17 feet long. We're pulling out from the bottom. It goes like this, and that comes down. Right? That's the gist of what's going on here. Okay, so let's go solve. So to solve this problem, we take our equation and we find the derivative of it with respect to t. Okay, go do that. I got 2x dx dt plus 2y dy dt equals 0. Okay. Remember, this is actually a lot like implicit differentiation when we found the derivative of y. Okay. But it's different because everybody is basically implicitly involved here because dt, the t variable, is inside each variable. Okay. Since we're out to solve for this, let's go solve that equation for dy dt, and then let's see if we can plug everything in. So solve this for dy dt. You missed all the fun stuff, Amy. There's no more fun stuff to do. Okay, I got negative x dx dt over y. Okay, the 2's can cancel. So that means for this particular problem, our answer comes from taking dy dt and evaluating it at x equals 15 and dx dt at 3. So what does this give us? Negative 15. And I highly recommend that you keep the units in here. So this is negative 15 feet times dx dt, which is 3 feet per second, all divided by, oops, I don't know why. We were so close. Okay, so at the moment x is equal to 15, we know what the value of y is. We can compute it. Okay, so it's 15 squared plus y squared equals 17 squared, and y is equal to 8. That's one of your triples that you should know, 8, 15, 17. 3, 4, 5, right? Seven, 24, 25, 9, 40, 41, all those good ones. Okay. So, notice what happens here with the units. The feet cancel. Okay. So when the feet cancel, we get negative 3 times 15 divided by 8 feet per second. And what is that? 45. Negative 45 over 8. Oops. Negative 45 over 8 feet per second. Give me a, what is that close to? Negative 5 and 5/8, which is 0.625. So this is what dy dt is. Okay. All right, negative 5.625 feet per second. What does that mean in the context of this problem? Yep. Right. This is going down, right? Remember with the ropes, since y is shrinking, it's negative. See that? That's why it makes sense that that number is negative. And that's how fast it's going. Its rate is negative 5.625 feet per second at this moment. Okay? Now, that's how you solve this problem. But I want to make sure that you understand this a little bit. What if I change this so that instead of being 15 feet away, it's only 2 feet away? Okay? At the moment where x equals 2. Okay? At the moment where x equals 2. We're going to make a prediction of just relativeness. This answer for that problem was negative 5.625. Okay? If I change the problem and I say, let's suppose it's only x equals 2, how is that answer going to differ, you think? Closer to 0. I heard smaller. Okay, so that number should be, I don't know what. Give me a number. That it should be closer to. Negative 1, we'll say. Okay, let's test it out. So I'm going to replace the numbers here with the numbers that we use in this problem. So dy dt, now with this new problem, it's negative 2 feet times 3 feet per second. And what number is going to go there? This is where you're going to need a little calculator action for that one. So it's 2 squared $16 point something. Seems like it'd be in that ballpark. 16. Let's just go 4 decimal places. 8811. 8819. Okay. So if I put in here 16.8819, do the math, multiply those two, divide it by that, and tell me what you get. Negative 0.554. Say it again. Oh, okay. Okay, and that's feet per second. My only reason for having us do this additional problem is to say, do you see how it makes sense? It should match up with the physics that you've learned throughout your life, which is kind of common sense stuff. Okay, that's what my point here is. So, and if I made x longer, if we went all the way out to 16.4, we can't go past 17. That's past the ladder. Then this thing would be going a lot faster. Okay? All right, that's the gist of that. Okay, let's read and set up the last one, number 5. The last one on that group. Has it been worth it yet?
Definitely.
Oh, good. Phew.
I can't imagine doing anything else.
Like sleeping,
Like sleeping,
resting.
Yeah. Letting my body recover.
Okay. Let's identify what we know, what we want to know, and the equation. So what do you got? Negative 0.3 centimeters per hour. That's something that we know. What does that mean? Negative 0.3 centimeters per hour. This is water evaporating out of this cone. What is it? dH dt. Now, let's just make sure, see if that seems right. The height of the water, okay, is given by h. If it's shrinking because of the evaporation, then it should be getting less, and it's measured in centimeters per hour. That looks good. Okay? All right, give me something else. Okay, so the height is 5 centimeters? No, that's the height of this one, okay? But that's the moment that we have. The initial height, initial... Yeah, so radius is 5 centimeters. That's the initial one here. This becomes a little bit tricky because we have to know, all right, at what moment this height is, and we have this height versus we've got this cone. So there's a connection here that we got to watch out for. Okay, what else we got? Or what else do we want to know? Yeah. Okay, 1/3 pi r squared h is the formula that relates the variables. And what do we want to know? dv dt. Okay, I think we got it. So dv dt, what does dv dt mean in this problem? How fast the volume here, the rate that the volume is changing by here, what is that rate? And notice that's a different number than how the rate that the height is changing by. Two different numbers. Okay. All right. Should we do this? Should we do the example first? Should we do that stuff before we do this stuff? Yeah, I think so. All right. We're going to play with the water right now because it's connected. Yeah. Yes, this is why we're looking at here. Okay. So, what does this have to do with anything? It's related to this problem here. Yes, that's the only good use of calculus books.
Yeah.
Okay, so for example, I'll take something simple. Okay, cylindrical base, right? Okay. So when I open this spigot and we've got water that's coming out, okay, this should fill up. If this is a constant flow, shouldn't the height rise at a constant rate? Right. So let's see if that actually works. Okay. What we're observing there is dv dt. Okay. The volume is changing, but then also the height is changing. Okay? And because the vase is cylindrical, it flows, the water, the rate that the height changes is a constant. Okay? If I did it for this one, it'd be a constant again. Okay? Do that. If I did it with this one? No. We would say that the height here would vary, have a variable rate, the height. Because it would be kind of slow at first, and then it would go up really fast. We've all done this, right? You've seen that. But you didn't realize that it was calculus that you were doing when you were filling up a funny shaped vase. I got to watch this one or else I'm going to make it go. All right, ready? So slow, slow, quick.
Someone want to take a drink?
Okay, constant rate, constant rate, and then variable rate for the height. The fun part is, the fun part is, what is dV dt for me filling the vase? What is the rate? It's constant. It's the same as this one. This one is negative because it's coming out of there. But this one is positive. It's the same number. dV dt is exactly the same. But dH dt, the rate that the height is changing, that one's different. We're just going to go ahead and leave that there. All right, what about this one?
What's the purpose of this? Candy, like sorry, no, okay, when Kayla was sitting here and she's like, that one over there kind of looks like a Christmas tree. I was like, yeah, like it's
Yeah.
but we thought it was a vase, but it's not.
It came with candies or something in it. Okay. So, I don't know. I'm going to try something different here. Okay. Now, maybe only the people who are close can see this, but it should vary, right? It should go slow and then quick and then slow and then quick, like that as we go through. So I'm going to try to pour this in at a constant rate. Is it noticeable or no?
Yeah.
So the intent there is that it's a variable rate for the height changing, okay? Because of how wide the glass was. Okay, and then last one, what about this one? Fishbowl. How should that one grow? How should the middle compare to the outer?
It would be the slowest point.
Should be the slowest point. In fact, the slowest point, the slowest rate should be smack dab in the middle, where it's at its widest. Okay. This is where it takes forever, and then it starts to speed up again. Then it has that sound that you can tell when it's getting up to the top. Ask Mr. Westby what that is. Okay, so now we have this. Okay, now we're going the other way. Now there's water in here and it's evaporating. Okay, so the HDT is the rate that the height is changing by, so the water's going down. And we want to know, hey, how much water, that's dVdt, how fast is the rate of water coming out of there? So let's go figure it out. I don't know what to do. What do you think we should do? Cry.
That's how you know. It's a nice Calvin Klein shirt.
Okay. I spy a problem. So, because r squared h, that product is part of the original formula, we have to use the product rule, but still use dt when we're finding the derivative. It's no big deal. So let's see, we'll let r squared be the first derivative, so it's 2r dr dt times h plus r squared times dH dt. And that's no big deal. Notice it's product rule. Derivative of r squared is 2r dr dt, and then we multiply by the h. Then the r squared sits out, and the derivative of h is dh dt. So that's where all the pieces come from. Okay, piece of cake. Let's just plug in what we know. So it's 1/3 pi times 2. Do we know a radius? Wait a second. We don't have a radius, but we do know that this is the height when it's 5 centimeters. Okay? Is it a half? Is this one 5 centimeters? Well, let me tell you what we can do. We can identify that in the initial one, the ratio of the radius to the height was equal to 5 to 10. Right? And that ratio stays constant here. So we're actually in good shape. This as 5 centimeters is correct. If it was something other than 5 centimeters that was harder to do, we would just plug in what we knew and then solve to get the other one. Oh, yeah, my bad. This radius was 5, therefore this one's 2.5. Did you see that?
Yeah.
2.5
I
there.
saw it.
Yeah, fix your glasses. So the radius is 2.5. Okay? All right, do we know dr dt? Okay, well, wait a second. We only know dh dt. How are we going to figure out dr dt? Okay, the radius to the height was 5 to 10, right? 5 to 10. Do you agree that as this is evaporating, the radius and the height should be related? So watch this. See this equation that I wrote that had to do with the r and the h? I'm gonna just rewrite this here, and I'm gonna say the rate is equal to 0.5 h. You know what I mean? Just cross multiplied there. Solve it. R is equal to 0.5 h. And remember a long time ago I told you that equations were born to be manipulated? Okay. Well, guess what? Even though this equation is a supplemental equation to this one, you can also take the derivative of this one with respect to t. So to solve this one, we actually have to find the derivative of this one, which tells you that dr dt is equal to 0.5 dh dt. So this is like a little baby inside of the one over there. Little baby equation. Okay, so dr dt, this one right here, is actually 0.5 times dh dt. So I'm going to put in 0.5, and we knew what dh dt was. It was negative 0.3. And I should put some units in here. This is centimeters. This was centimeters per hour. 2 times radius times dr dt times h, and h was 5, plus r squared, which is 2.5 centimeters squared times dH dt. 2.5, that's what I said. Wait. Oh, yeah. That was that original. I was looking at the wrong one. Multiplied by dH dt, which we figured was negative 0.3 centimeters per hour. And that's all we got to figure out. Okay, we're going to run out of time. Get me an answer here. And tell me what the units are right now, though. What are the units? I can tell by looking at this. It's dV dt, the rate of the volumes. It's cubic centimeters per hour. Okay, bring me an answer tomorrow, and then we're going to look at the last two. And then we're going to play with sand tomorrow.